Okay, so yeah, today I'm going to talk about knowledge graphs. And actually, knowledge graphs are really just the latest incarnation of knowledge representation and reasoning, which has a very long history, which I should just mention something about perhaps at the beginning. I could even go back as far as the Greek philosophers and talk about things like Aristotle and the tree of Porphyry and so on. But as time is short, I'll skip forward a bit and move to the early exploration of AI, which, for example, the general problem solver from Newell and Simon, which was trying to capture problems by representing them using logical sentences and using a theorem prover to solve general problems represented in this way, which we can already see as an early form of knowledge representation reasoning, really right at the beginning of the computer era and AI. And similarly, expert systems that followed shortly after, the idea there was to try to capture expert knowledge about some specific domain and to sort of simulate expertise and to be able to answer questions about the given domain. And if we look at the architecture that was described at the time for expert systems, we can see that we already have all of the components we would expect in a modern day knowledge representation and reasoning system. We have knowledge captured in some sort of knowledge base consisting of rules and facts. We have an inference engine, and we have a user who can ask queries and gets answers back from the system, where the answers depend on the stored data, the knowledge and the rules and the facts, and the questions are answered over those rules and facts by an inference engine. So here we have knowledge representation and reasoning already at this early stage of AI. So why use a graph for knowledge representation? Well, just jumping back briefly to our friends, the Greek philosophers, we can see that the idea of using a graph is also very old, and it's very natural really to represent this kind of knowledge as a graph. Here we have this representation of the kind of animal kingdom, and the graph breaks that down hierarchically into more and more specialized classifications. It also represents the differentiae, the things that differentiate increasingly specialized categories. And in fact, graphical forms of knowledge representation, such as this, were there in the very early days of knowledge representation and reasoning. They were called semantic networks. And if we come more up to date, it's actually very natural to think of the World Wide Web as being some sort of graph-like structure where we have web pages that are linked together via URIs. And this idea actually motivated research into the semantic web, where the basic idea was to introduce standards for knowledge representation on the web so as to transform this linked page structure of the World Wide Web into something more like a distributed semantic network. And out of this idea came the development of representation languages for using on the web, including RDF and OWL, and a suitable query language for using on the web, which was Sparkle. And if we come right up to date, of course, we have the famous Google Knowledge Graph, which is now increasingly used by Google. Most times when you ask a Google query these days, it will come up with a little info box at the right-hand side. It might even answer your query directly if you ask it a specific question. like how tall is the Eiffel Tower, it'll actually come back with some number of meters, and it'll show you a little info box on the right-hand side that gives you other information about the Eiffel Tower and related things. And all of that is coming from the Google Knowledge Graph. And we can see knowledge graphs in these kinds of applications now all over the place. So all the e-commerce people have their knowledge graphs capturing all the huge array of products that they sell. And personal assistants have knowledge graphs embedded in there, capturing information about the domains in which they're operating. And we see them increasingly in industry also. So next, I'm actually going to cover a little, introduce a little running example, which I'm going to use just to explain what I believe a knowledge graph really is, and just to make sure that we're all on the same page about that. So what does a knowledge graph look like? Well, it looks like a selection of entities and values that are relevant to the domain in question. So here we have things like buildings, the Eiffel Tower, London, 310 meters. All of these are vertices in the graph, and these are connected by labeled edges, which were the labels describe the relationships between the different entities. So for example, here we have London is the capital of the UK, the Shard is located in London, and so on. In RDF, a single edge with the entity or value at either end of the edge is called a triple. And the entity, the source entity is called the subject. The edge label is called the predicate, and the target entity is called the object. So that's in RDF. It's useful, I think, to notice the fact that in a way, there's nothing so incredibly special about this graph form of representation. We could have used a database for capturing this information pretty much equivalently, using, for example, tables like these ones you see on the right, where we have a table for cities, which has Paris and London in it, a table for building, a table for tower and architectural structure, and so on. And this actually captures pretty much the same information that we have in the graph. But a big advantage of the graph is it's much more intuitive, and I think this is one of the reasons why graphs were used in the very first place to represent knowledge. For example, we can see all the relationships directly in the graph. We don't need to know about foreign keys in order to understand how the information is really structured. If we pop back to our relational tables example, actually, without knowing about these foreign keys, it's pretty hard to understand how all of these tables were related to each other and sort of reconstruct the knowledge that was really captured in a much more intuitive form in the graph. Another interesting thing to notice about the graph is that this kind of information, which is often called the part of the schema in a database, this kind of information is captured directly in the graph. So this upper part of the graph here that I've circled in, I've outlined in blue, this actually represents part of the schema of the knowledge that we have here, or at least the sort of taxonomic backbone of the schema, and it lays out the structure of the domain that we're talking about, where we have architectural structures, of which there are towers and buildings, and we also have cities. So that's the basic schema we're working with. And actually, if you recall the database case, this corresponds quite closely to the table structure. But now we have it as a kind of first-class citizen in the graph, and we can manipulate it directly, the same as the data. I'm talking of the data. In this picture, the data sits in the lower part, and this was in the database case, this was kind of the content of our tables. Another interesting thing is that in the graph, each entity appears only once in the graph, and it can be arbitrarily connected to other entities in the graph. In the database case, actually entities can occur multiple times in different tables. For example, Paris is in the architectural structure table and also in the city table. And the links between the different entities actually use string matching. So in the database, these are actually just strings. And to know that this string here, this entity here matches to this entity here via the foreign key, we actually have to look at the two strings and figure out that they are matching. In contrast, in the graph form, we have Paris occurring only once, and it can be arbitrarily connected to other entities in the graph. Moreover, in the graph, typically these entities are not represented by strings, but by URIs, so they have a unique identifier. And these URIs can even reference knowledge in other graphs. For example, in this case, the architectural structure, we might actually use the Wikidata URI for architectural structure. And then if we want to, we can actually enrich this graph we have here by linking a whole bunch of additional information about architectural structures that we can directly access via this URI in Wikidata. Another thing about the graph form is that it's much more flexible and extensible. Databases are notorious for the rigidity of the table structure, and if we decide we want to add some additional information, for example, we might decide that we want to add architects, information about architects. In a graph, this is really easy. We just add the relevant additional entities, the architects themselves, and we can link them in an arbitrary way to the entities, so we can have multiple architects for a single building without any problem, and so on. Of course, we can also trivially delete information from the knowledge graph, and the eagle-eyed amongst you might have noticed that this knowledge graph is already a little bit out of date, and there was an edge here at the bottom which represents the UK's membership of the EU, which sadly no longer holds. So we really should delete that. And of course, that's easy as well in a knowledge graph. We can just delete edges when facts no longer hold. So this is kind of trivial and obviously also easy in the database case, but there are some interesting consequences of this when we talk about reasoning, and I'll come back to that a bit later. And finally, another thing about graphs that can be quite useful is that they facilitate other kinds of queries, such as navigation. We can just, find information by just sort of traversing around the graph. Then we can do things like similarity and locality and so on. So these can also be quite useful. Okay, so far things seem to be look quite good for this graphical form of knowledge representation, but of course there are always challenges. And one of the challenges that was observed very early on with semantic networks is that the name was kind of ironic because they were very vague with respect to their semantics. So in a seminal paper back in 1967, Quillian pointed out this issue and he gave a little example fragment of a knowledge graph, or semantic network as it was called back then, like this, and sort of focused in, for example, on this particular triple here, cat has color black, and said, well, in this semantic network, the meaning of that is completely vague, and one could imagine many different meanings. I mean, it could mean that all cats are black, it could mean that some cats are black, or perhaps it could even mean only cats are black. And so, there was really nothing to say in the network itself which one of those meanings was intended. And if we come back to the running example of a knowledge graph, we can see where this problem sort of bites us. If we want to answer a query over the knowledge graph, which says, retrieve all the architectural structures that are located in the EU. So if we look at the graph, intuitively, we think we ought to be able to answer that question. I mean, we have architectural structures here. We have, at least a couple of them represented in the graph, and we have their locations, and, we have all the information in the graph we need to answer that question. But from a sort of computational point of view, actually, it's not so easy to understand how we would really answer it, because the information is intuitively there, but the semantics isn't clear. For example, in order to answer it, we have to make some assumptions about the semantics of type edges and kind of edges. So we probably imagine that if the Eiffel Tower is a tower and a tower is a kind of architectural structure, then the Eiffel Tower is also a type of architectural structure. But this isn't explicitly stated in the graph. So again, answering the query becomes difficult. And similarly, in order to answer the query, we need to make some assumptions about the semantic relationship between location, capital of, and member of edges, where we might intuitively think that it should imply some, additional facts like the ones I've shown here in the picture. But none of this is explicitly given by the graph in its kind of basic form. So how to solve this problem? Well, luckily, philosophers, mathematicians, and computer scientists have been thinking about this problem for a very long time, and long since came up with a ready-made solution for us, which is, of course, logic. So what we can do is we can just establish a direct correspondence between the graphical form and a logical form. And this is actually very natural and very straightforward. So for example, these kind of edges in the schema part of the graph, we treat them just as being logical sentences of this form, which basically just capture the inclusion relationship. So this just says for all x, if x is a tower, then x is an architectural structure, and similarly for buildings and architectural structures. And then for the data part of the graph, we can just treat this as basic ground facts in the logic. So all of these edges in the graph just translate into ground fact statements in our logic. And this has very many advantages. Well, sorry, the whole thing taken together now is a knowledge graph, and the graphical part here on the left can be thought of as just completely equivalent and interchangeable with the logical part on the right. So the logical representation on the right, the two things are saying exactly equivalent. So one of the additional advantages is that once we decide that we're going to use logic to represent the schema part of the graph, actually we can use additional, more complex logical sentences to capture additional knowledge that actually isn't quite so easy to represent in the graphical form. Although in OWL, there is a kind of graphical representation of these more complex axioms, but we don't have time to go into that today. But the point is that we can use more powerful logical sentences to capture these additional constraints. So here I have two more sentences that explicate the semantics of these relationships between location, capital of, and member of that we intuitively imagined when we were thinking about answering our query about architectural structures located in the EU. So an additional very nice feature of using logic to capture these, to capture the graph, is that this also gives us completely naturally and for free, as it were, a semantics for query answering, which is just logical entailment. So for example, we can see that the Eiffel Tower is in the answer to our query for architectural structures located in the EU. We can compute that, and it's in the answer just because our logical form of the knowledge graph shown above here actually entails the two atoms, Eiffel Tower is an architectural structure, and the Eiffel Tower and the EU are in this location relationship. So that's entailed by our facts and our axioms in the logical form above. And we can equivalently think of this as that the logical form entails the additional edges that we were intuitively imagining when we were thinking about answering the query over the knowledge graph. And I'll come back to this idea of entailing additional edges when I talk about actual reasoning procedures in a bit. Okay, so yes, we can, so logic gives us a natural way of defining how queries are answered, which is just logical entailment. And moreover, you know, we can just look in our textbooks and find some nice algorithms for actually computing logical entailments. For example, we could decide to use natural deduction rules, and one of those rules we can use directly to compute the fact that the Eiffel Tower is an architectural structure. And we can even find proofs in our textbooks that these algorithms are really doing what they're supposed to do. They're sound and complete, and they always give us the right answer. So all this looks really great. So did we solve the problem? Well, of course, in computer science, things are never quite as easy as we would like them to be. And the problem here is that logical reasoning in general is can be a very hard problem. And in particular, it was famously proven that the first order logic entailment problem is actually undecidable. So there's no algorithm available that can guarantee to compute logical entailments for arbitrary input first order logic sentences. Moreover, even if we use a less expressive logic that's actually decidable, reasoning may still be of very high complexity and take a very long time. So even propositional logic, for example, is famously NP-complete. I mean, it's really the sort of canonical NP-complete problem, propositional logic satisfiability. So what to do about that? Well, we obviously can't change these complexity results, but what we can do is take a more nuanced view of them. And in the first place, we should understand that these are worst case results. So even if the logic as a whole is undecidable or intractable, it doesn't mean that we can't quite effectively solve some problems in that logic. And it may be the case that in realistic applications, the actual problems that we are called on to solve turn out to be actually not so difficult. Another thing that we can do is that we can study knowledge representation languages, the logical formalisms, and we can try to find a language that has a good balance of expressive power and computability. So we don't choose a logic that's too powerful so that we can't compute anything in it, but we try to find one that allows us to express most of the things that we'd like to express in our applications. And then we'd like to design reasoning algorithms that work well in the kind of typical cases, as I was describing above. If our logic isn't worst case tractable, it might still be the case that we can design smart algorithms that exploit the features of typical cases to work quite well in practice. And we could use such algorithms to build highly optimized implementations that we hope will work for us in practice. So these ideas are exactly the ones that were the basis for the research area of description logic. So description logics are a family of logic-based knowledge representation languages. They're usually decidable subsets of first-order logic, and they're actually usually inside one of the well-known decidable subsets of first-order logic. In particular, the subset of first-order logic that has counting quantifiers, but at most only 2 variables, which is called the C2 fragment of first-order logic. And the idea behind description logic is that the family provides a whole bunch of different constructors, the Booleans, for example, restricted forms of quantification, some counting quantifiers, and a whole load of other things. And then you can design a specific description logic basically by selecting a subset of these constructors. And within the field of description logic, people have spent a long time exploring a lot of different combinations, ones that look useful, and also hopefully trying to find ones that have this good balance between expressiveness and complexity. And for several description logics that seem to hit these kind of sweet spots where they're quite expressive but not too intractable, then people have built highly optimized reasoners that exploit the features of realistic knowledge graphs and that have been shown to work quite well in practice. So coming back to the semantic web, which I mentioned before, the goal of which was to sort of try to transform the web into something more like a kind of huge distributed knowledge graph. And I also mentioned that as a first step in this endeavor, knowledge representation languages were designed for use on the web. And these languages were actually based on, well, OWL anyway, the schema language was actually based on a description logic for exactly the reasons I was just mentioning in the previous slide, that in description logic, there was already, well, for one thing, a very clear semantics, because it's just a fragment of first order logic. So basically, it just inherits the semantics of first order logic. And we knew a lot about the different languages, expressive powers, computational properties, and we already had quite effective reasoners that we were hoping we could use to sort of, jumpstart the whole process of developing this kind of semantic web idea. So that all was going quite well, but of course, as I mentioned before, things in computer science, it's always a bit of a roller coaster ride, as those of us engaged in research know. It's looks good one day, but then the next day you find out there are some additional problems. And in the semantic web endeavor, I guess the issue was that things went very well for ontology-centric applications with this kind of existing description logic reasoner approach. So there was very successful use of these kinds of reasoners and the OWL ontology language for developing ontology-centric applications. So these are applications where the main focus is actually on constructing a very large schema. And these can be pretty large. I mean, some schemas, ontologies that I've seen have hundreds of thousands of classes in, but that's pretty much the limit. I don't think I've ever seen an ontology with more than 1 million classes in it. And the main reasoning task in these kinds of applications is computing the taxonomy, so the subclass-based hierarchy of these different classes or concepts, as they're sometimes called, in the graph or ontology, as it's often called. And OWL, DL-derived OWL reasoners such as Hermit and ELK were used for this process. And as I say, they were very successful. They can help to identify errors and inconsistencies. And actually, for example, in the case of the SNOMED ontology, which is a very large scale ontology that's used widely in medical systems in more than 80 countries. Actually, there's an international organization that works on developing SNOMED, and as I say, it's a standard that's used in healthcare systems of many countries, including the UK, possibly Norway, I'm not sure, but I think so. And this, they use DL reasoners on a day-to-day basis in their development of this ontology, and it's a big success story. What wasn't quite so successful was the use of such reasoners in data-centric applications. The trouble here is that the scale is just different, for one thing. So typical graphs sort of that have more data in them, the size of those can be almost arbitrarily large, and there are many graphs out there that have billions of edges, even tens or hundreds of billions of edges in the case, for example, of the Google Knowledge Graph. Also, the reasoning task is different. So here, the main task is not organizing the class hierarchy. Here, the main task is answering SPARQL queries over the data. And the existing OWL DL reasoners didn't scale so very well to this task. The problem being that query answering actually reduces to multiple entailment checks. So basically, you have to, for every possible tuple that might be an answer, you have to check whether the query with the tuple substituted for the variables, whether the resulting ground sentence is entailed. That means that that tuple is then one of the answer tuples. And there could be very, very many such candidate answer tuples. In general, the number of those could be polynomial in the size of the graph. And each individual entailment check could be very costly because you might have to work with this whole huge graph to check the entailment. So that just wasn't really practical. So in OWL 2, which was a revision of OWL that appeared, I think, in about 2012, if memory serves me correctly, one of the new things that was introduced there were profiles. And OWL profiles were subsets of OWL that had better computational properties, and in particular, were even worst case tractable. So 3 profiles were introduced. One was called QL, and this was based on the DL Lite description logic. One was called OWL2EL, which was based on the EL description logic. And the third one is RL, which is based on a fragment of description logic that's actually the intersection between description logic and data log. So what you can represent in this language is exactly the sentences that you can represent in both data log and description logic. The other thing about these profiles is that the logics in question allowed for different algorithmic techniques that were much better suited to query answering. So in particular, the QL language was actually specifically designed so that it could use an algorithmic technique called query rewriting to perform query answering. And in the RL case, we can exploit materialization techniques from data log, and there's a similar approach for the EL profile. So it'll be interesting perhaps just to very briefly explain how those techniques work. In the case of query rewriting for the LQL language, how this works is it just uses the ontology to expand the query until the expanded query over the graph without any additional schema knowledge gives the full answer to the query. So for example, if we're just asking for architectural structures, it's pretty easy to see that we have these 2 axioms that say tower and building are a subclass of architectural structure. Here I've represented them in the description logic form, but we could equally well write them in the first order logic form, as I showed on an earlier slide. And we can use those just to expand the query into a union query where we say, well, if I'm going to answer this query for architectural structures, I also have to include towers and buildings. And basically, I use these axioms as a sort of backward chaining rule to do this rewriting. So this expanded query now, I can use that over the original graph without further reference to the ontology in order to answer the query. And if I answer that, I'll get the correct answer. Another thing is, actually, if the data is really sitting in a relational database with a structure like the one I showed you back in the introductory slides, I can even take this expanded query and transform it into SQL, like I'm showing here, and I can answer that SQL query over the actual relational form of the graph. So I don't even need to, if I have my data sitting in legacy relational stores, I can actually answer a kind of graph-based query with an ontology directly over the relational store using this query rewriting technique. So this obviously is really nice and has, many advantages, but the problem with it is that in order to be able to use this rewriting approach, we can only have a very weak ontology language, which doesn't give us much more than this sort of taxonomic backbone. And for example, I wouldn't be able to rewrite the query asking for architectural structures located in the EU because I can't capture logical sentences like this one that talks about the relationship between location and capital of, because it's recursive. So location occurs both in the body of the rule and in the head. So if I try to rewrite using this, I'll end up with a non-terminating rewriting, or equivalently an infinitely large query. Okay. Moving on to materialization. So this takes the sort of opposite approach. Instead of expanding the query using sort of backward chaining over the ontology rules, it expands the data using forward chaining with the ontology rules. So if I want to answer the same query here, what I do is I treat the axioms as in this kind of rule form here, and I do sort of forward chaining over these rules, which is actually called the chase in Datalog. So I just apply these rules exhaustively, and I just materialize the answers into the graph. So what would happen here is I'd actually introduce these two new type edges, and then I can just answer my original query over the expanded graph, and I'll get the answer that I'm looking for, which is the Eiffel Tower and the shard. This approach has the advantage that it's equally able to deal with the more expressive rules for capturing the relationships between location and capital of, and location and member of. So I could forward chain using these rules and actually materialize these additional edges in the graph, and then I'd be able to answer my query for architectural structures located in the EU. One issue with this approach, however, is the fact that that if data changes, in particular if the data is, if facts are retracted, for example, coming back to my case where we have to delete this edge here, which represents the UK's membership of the EU, then we would really like to, so some of the entailed edges now become invalid. In particular, this edge here is no longer entailed. And actually retracting knowledge and then updating the entailed edges is not trivial. It's a process that's often been called truth maintenance. And I can actually use a similar approach for EL, but as time's a little bit short, I won't go into the approach for EL, but basically I can use the same materialization approach with a bit of extra complexity to deal with some issues in EL. So this idea of a materialization-based approach seems to be pretty promising. Materialization reasoning seems to be really ideal for these data-centric applications. We can support a quite expressive ontology language, so we seem to be in this sort of sweet spot space that I was talking about before, and we can also have very fast query answering over very large graphs, because we do all of the real work offline ahead of time, materializing all of these edges into the graph. So we do the reasoning as a kind of one-off pre-processing task, and the cost of that is amortized over an arbitrarily large number of queries. And at query time, we're really just back to the sort of database situation where we just have to answer the query over the kind of data that we explicitly have. Of course, there are some challenges. So materialization can be costly, both in terms of the time it takes and memory. So it's an offline task, but still, if it's going to take hours or even days, that might be infeasible. And in particular, it might be problematical if the data is changing a lot, because in many existing materialization systems, as they were back then, they didn't support truth maintenance. So if you retracted any fact, you basically had to throw away all entailed edges from the graph and recompute all the entailed edges from the scratch, which could take hours or even days on large graphs. So this motivated our research into RDF-Ox, where the basic idea was that we wanted to build a highly optimized materialization-based reasoning system that exploited modern architectures, in particular the fact that modern machines typically have pretty large memory, so we can actually keep a pretty large graph in memory, and they have multi-core processors, so we can try to speed up some of these reasoning processes by exploiting parallelization. And we also wanted to build the system from the beginning so that it would support this incremental reasoning. So we didn't have the problem that if the data was changing, then basically it was really infeasible to use the system because we'd have to keep starting again from scratch. Another thing that we wanted to do with RDF-Ox was that we wanted from the beginning to build it based on algorithms that were formally proven to be correct, in the same way I was describing for logical reasoning in general. We wanted to exploit that advantage that we were using algorithms that we knew were doing the right thing. And this actually proved to be really critical, because when some consultants did a comparison, this graph here doesn't come from work that I did. It was given to me by a consultancy that did a little comparison of knowledge graph systems. What they discovered is that many other graph database systems, knowledge graph systems, are just broken. I mean, if you give them a bunch of queries, they'll typically crash, timeout, return wrong answers, all sorts of things. And this is because many of them were developed using traditional software engineering techniques where you just try to kind of correct the algorithm via testing and debugging. And that's really difficult, if not impossible, I would say, for these complex logic-based algorithms. Another thing is performance. Although RDF-Ox is correct, it's also actually proved to be much faster than many of these other systems. I mentioned already that we used an in-memory approach for RDF-Ox. So actually, if you think about it, when you're answering these queries over the materialized knowledge graph, actually, you already have all of the data, and the query answering process is really very much the same as in databases, where you have to do a lot of joins to identify the two different atoms in the query, in an answer to the query, that kind of match up according to some of the variables in the query. And in order to do this efficiently, you need to store the triples in a data structure structure that allows it to be accessed in different orders, for example, in subject order or in object order. And you also need indices that allow you to jump into one of these orderings at some particular point. So in RDFOX, we developed this novel data structure, which we actually patented, which stores all of the graph in memory. And it's designed in such a way that we can exploit the compare and store instructions that multi-core processors have in order to update the data structure without locking. So most of the operations on this data structure are completely lock-free, which allows us to exploit multi-core parallelization. Obviously, storing the graph in memory imposes certain constraints, but with modern machines with pretty large memories, even in a fairly basic machine, we can typically store 1 billion edges, even just in a laptop. And in a more powerful server, we can store tens of billions of edges. And this actually turns out to be more than enough for many applications. Oh, sorry, I'm going in the wrong direction there. So I'm nearly done. I'm a bit unsure about the time constraint here. I'm thinking I've got an hour, but I'll just double check with you.
Yeah, so Iran can take maybe 5 more minutes and wrap
5 more minutes, that's perfect. I'll be done in 5 minutes. Okay, so as I mentioned, we can materialize in parallel, and on typical benchmarks, we get speed ups of up to 20 times, even on just a 16-core machine, because we can exploit hyper-threading to actually use the cores more efficiently. And I just wanted to lastly mention incremental addition and retraction. So as I mentioned, we have a novel algorithm for doing this incremental maintenance, and this also brings about a great improvement in performance. So the last thing I just wanted to mention was a sort of interesting experience that we had with RDFOX, which was that we decided to commercialize RDFOX via a spin-out company called Oxford Semantic Technologies because it was proving to be quite successful and a lot of companies wanted to use it, but we couldn't really support that as a research group. So we needed a company to support it. And it turns out that when you try to take a research piece of software and commercialize it in a company, a whole bunch of additional challenges emerge that are more prosaic, but nonetheless real. I mean, for one thing, we actually had to extend the representation language quite a bit. And because I'm a bit short of time, I won't go into the details. But for example, in realistic applications, there's a lot more focus on data types like numbers, strings, dates, and so on. So we had to add a whole load of kind of built-in functions for, you know, extracting the year from a date and aggregating numerical values and so on. And we also had to add support for languages such as Shackle, which allow for capturing constraints via a sort of negation as failure extension to the language. We also had to do a lot with the system architecture. So RDFOX as a sort of research piece of software was pretty basic. It just really had the reasoning engine and a command line interface. And when we commercialized it, we had to build a whole raft of infrastructure around that in order to satisfy real customers. Okay, so I had a few use cases that I was going to mention, but in order to keep a bit better to time, I'm just going to mention one particularly interesting one, which is configuration management. So RDFOX is actually being used at Festo, which is a large company in Germany that sells production line equipment. And they use RDFOX for checking that for help supporting engineers in constructing these very large and complicated production line setups. and capturing expert knowledge about compatibility between different components. And I don't have time to go into the details, but it's just quite interesting to notice that this actually comes back quite close to expert systems, which were one of the ideas that emerged very early on in the days of AI. But it's taken us all of this time to basically develop knowledge representation and reasoning systems to the point where they're actually able to support an expert system really at scale in a realistic application like the one at Festo. So yeah, there are a few more examples here which you can look at in the slides, which will be available offline. So I'll just jump to the kind of summary, which is that, well, knowledge graphs are a powerful tool. There are many applications. There are, of course, a bunch of technical challenges, which I've alluded to. But I think by now we've found solutions to most of those technical challenges, which are based on a combination of foundational research and solid systems engineering. So all that remains is to say thank you to a bunch of people that I've been lucky enough to work with over the years, and say thanks for listening, and I'll be happy to take any questions at this point if there's time for that.